Hello, geometry students. This is Miss Moore here giving you another virtual lesson. Today's topic is special right triangles, more specifically 45, 45, 90-degree triangles. Let's get started. Where does the name 45, 45, 90 come from? Well, it comes from the triangles quite literally having 45 degree, and 90-degree angles. If you can remember, these triangles actually have another name as well. Think about the most specific name for this triangle. You got it? That's right. It's an isosceles right triangle. So let's break down this name real quick and think about some things that come to mind. Well, I'm going to look at right triangle real quick. Okay, when I think about a right triangle, first thing I think of, Pythagorean theorem. So I went ahead and labeled these sides A, B, and C. A and B because they're the legs, and C is always our hypotenuse. Pythagorean theorem, if you remember, is A squared plus B squared equals C squared. Awesome. Now let's break it down to the other part, right? So we also have this word isosceles, right? What does isosceles mean? Well, it means that these two angles right here are congruent. Oh, I can't believe I just erased that. Sorry. This angle right here is congruent to this angle right here, and there's something else on here that I haven't marked off. These two sides must be congruent as well. If I know these two sides are congruent, can't I just set them to the same variable? So, for instance, can't I just say B is equal to A? Yeah, right? They're the same side. You might as well make them the same variable. So I'm going to change B to be equal to A. And if I do that, that's actually going to change up my formula over here a little bit and help me solve, right? So I'm going to go ahead and I'm going to say that instead of B squared, I'm going to say A squared, right? And then everything else will stay the same. So I've got A squared plus now A squared, and that's still equal to my hypotenuse squared. This gives me the opportunity to combine some like terms. I can combine A squared and A squared. That gives me 2A squareds plus C squared. Ooh, I could pretty easily solve for C here now. So I'm going to do that. So if I want to get C all by itself, I'm going to have to take the square root of both sides. C squared is just C. Product property of square roots allows me to break this up into root 2 times the square root of A squared. I don't know the square root of 2. It's an irrational number. So in order to keep all those extra long decimals in, I'm going to keep it as the square root of 2. So here we go, square root of 2. I know that the square root of A squared is A. That's going to be equal to the hypotenuse. And I'm just going to reorganize this so it looks nice. And I'm left with A times the square root of 2 is equal to C. Well, what does this mean to me? Well, this means to me, if I read this out, the hypotenuse is equal to the leg times the square root of 2. So the hypotenuse is not only equal to C, but now I can set it equal to, put it in blue like we did with A. So what does this mean to me? Well, it means that the hypotenuse is equal to the leg times the square root of 2. Now let's rewrite this on the triangle as well. I'm going to write it in blue. That means the hypotenuse is not only equal to C, but it's also equal to the leg times the square root of 2. Can you see what's happening here? If not, let me erase some of this stuff and help you see. And this actually might have been something that you already noticed, maybe when we did the Pythagorean theorem before. So let me rewrite this. We said that the two legs were congruent to one another, and we called them both A. Instead of A, I'm just going to use X now, just as something nice, something uniform that we can just kind of look at from here on out. So as I write this, I want you to copy this down or pause the video when I'm done, because this is a really important formula that's going to save you a lot of time in the future. So if this is a 45, 90-degree triangle, if it's an isosceles right triangle, We know that it's isosceles by these two being 45, or also the sides being marked off here as congruent, right? And most importantly, to this right angle here. All right, so I said I'm going to use X now instead of A. And what we just found out is that whatever these two sides are, whatever those two sides are, the hypotenuse is always that side times the square root of 2. Again, you might have noticed this back when we were doing Pythagorean theorem, and you might have wondered, I wonder if there's a pattern to this. And yeah, there is, and this works out anytime you have an isosceles right triangle. It's really important that it's isosceles and it's a right triangle. This does not work for all isosceles triangles. This does not work for all right triangles. It only works for isosceles right triangles, or 45, 45, 90-degree triangles. Now let's put this to use with an example. Here's an example here. And let's say in this example, I'm given that one of the legs here is equal to 6 units. Well, you know, this video is about 45, 45, 90-degree triangles. Do I know that this is a 45, 45, 90-degree triangle? In other words, am I given enough information? Yeah, actually, I do know this is a 45, 45, 90-degree triangle, because if this angle right here is 90 degrees, and this is clearly an isosceles triangle because these two sides are congruent, that would mean that this angle and this angle would have to be the same, and they'd also have to add up to 90, so they would have to be 45, 45, 90 degree. Now, I know it's 45, 45, 90 degree. I'm going to write my formula over here in the corner so I can quickly solve this. One thing I suggest doing is to write this on your papers when you know you're working with these special right triangles, just so when you get to those problems, you can quickly kind of use this formula. It eliminates some mistakes as well. So now looking at this formula over here, I know one of my legs is 6. That means my other leg here is going to have to also be 6. So I'm going to write 6 down. And if I know that these two legs are 6, I know my hypotenuse is always the leg times the square root of 2. So my hypotenuse would have to be 6 root 2. And that's it. I just wanted to find the other sides of the triangle. Instead of going through the Pythagorean theorem and using all of that time, I've now eliminated that, and I get to solve it really quickly. Let's try another one. All right, here's another way you might see an isosceles right triangle. So here's what I'm given in the problem. The problem tells me that this side right here is 3 root 2, and I want to find the other sides of this 45, 45, 90-degree triangle. Good thing I left this formula up here. It's going to save me some time. Now I need to figure out what side this is. Is it one of my legs? Is it the hypotenuse? Well, the hypotenuse is always opposite the right angle, and here's my right angle. It must be the hypotenuse. So I'm going to go over here and look at this diagram that I made, this formula that I have. And really quickly, I can see that my hypotenuse is x times root 2. Now, x is the number that's attached to my root 2. In this case, that number happens to be 3, which means these two legs are also equal to 3. And I'm done. I've done what I was asked to do. I was asked to find the other sides, and here we are. Let's do one more example, maybe something we got to think about. Okay, so here in this example, we have our hypotenuse is 8. Well, again, I've written this formula down in the top, and the pattern tells me, or the formula tells me, that the hypotenuse is always some number times root 2. And in previous examples, it was really easy to pick out what that number was. But in this one, what's challenging is that root 2 isn't there. Well, the way we're going to do this is we're going to set up an equation. Since the pattern is always true in these 45, 45, 90-degree triangles, that the hypotenuse is equal to x times root 2, I'm going to set this hypotenuse equal to x times root 2. That way, I can solve for x. So 8 should be equal to some number times root 2. I have an equation I can solve. So I want to solve for x. I want to figure out what that number is. I'm going to divide both sides by root 2. That's going to cancel out these root 2's and leave me with x on the right side and 8 over root 2 on the left. But we've talked about this before, is that you can't have a square root in the bottom of your fraction. So we need to rationalize the denominator. In other words, we need to make it so there's no square root in the bottom. In order to do that, I'm going to multiply the top and the bottom by root 2. Because root 2 over root 2 is really just multiplying this fraction by 1. So when I do that, I'm left with 8 times root 2 in the top, and root 2 times root 2, right, because we multiply across. Root 2 times root 2 is just 2. So x is equal to 8 root 2 over 2, but I can simplify this fraction. Means I'm going to get a 4 on the top, divide the bottom by 2 as well. I'm left with x is equal to 4 root 2. Which means this side is 4 root 2, and same with this leg. And I have found all of the sides. If you want to test this out, you can certainly go ahead and plug this 4 root 2 in for x root 2. And actually, let's do that. Let's watch what happens. So I'm going to test to see that this pattern's going to work out. I'm going to plug in 4 root 2. Right? That's my x times root 2. Well, when you simplify this, root 2 times root 2 is 2. 4 times 2 is 8. It all works out. The pattern holds. I hope you learned something new today, and if you have any questions, reach out to your teachers. Good luck this week.